Okay, imagine you're a scientist trying to crack the code of a really complex quantum system, maybe exotic materials or intricate molecular structures.
Yeah.
The way electrons or spins interact is just so complicated. Our best traditional methods often just grind to a halt.
Absolutely. I mean, the sheer number of particles, potential configurations, finding the exact quantum state, it's often just impossible computationally.
Right.
And that's exactly why tools like neural quantum states or NQS have become so important. They basically use neural networks as these powerful, flexible trial wave functions to approximate these states.
So using machine learning to give us a kind of educated guess that's way better than simpler approximations.
Exactly.
But here's the thing, right? Typically, we build these NQS using standard neural networks, and those are designed to operate in flat, familiar Euclidean space. You can think of it like modeling everything on a flat grid.
hmm And what if the structure of the quantum system itself, what if it isn't inherently flat? You know, what if the interactions, the correlations between particles actually have a more complex shape, maybe hierarchical or tree-like?
And trying to model that on a flat grid might be like forcing a round peg into a square hole. It just doesn't quite fit.
That's precisely the question. It might be forcing it into a shape that isn't natural for the system, and that fundamental question is what this new paper we're diving into today tackles head on with a really novel approach.
Okay.
Yeah, the core innovation, the real headline here, is the introduction of the first type of non-Euclidean neural quantum state. They've actually designed an NQS that operates in hyperbolic space,
Hyperbolic space.
using something called a hyperbolic gated recurrent unit, or HGRU.
Non-Euclidean space. Like we're leaving behind the flat world we usually do our computations in.
Exactly. It's a fundamental shift in the underlying mathematical geometry of the network itself.
Wow.
And we're going to unpack exactly what that means, how you even build a network that works in curved space, how they tested this idea, and importantly, why it shows such exciting potential, especially for systems where that kind of structure mismatch might be holding back the standard NQS methods.
All right. And our sources for this deep dive are the paper itself and a helpful study guide breaking it down. So let's jump in. But first, maybe a quick refresh. NQS using Variational Monte Carlo, VMC. Why are NQS so crucial and how does VMC actually train them?
Sure, so like we said, calculating the exact wave function for these many-body systems gets computationally intractable really fast beyond just a few particles.
Right. Exponential scaling.
Exactly. NQS offer a way around this. They use the huge parameter space of a neural network to represent a highly flexible trial wave function, an ansatz, as it's called.
The educated
A
guess.
educated guess, yeah. And this ansatz can capture the complex entanglement and correlations that determine the system's lowest energy state, its ground state, much better than simpler guesses could.
Okay, so the network is our guess for the wave function. How does VMC figure out if it's a good guess then?
VMC is the training loop. It's the optimization engine. The core idea comes from the variational principle in quantum mechanics,
Okay.
which basically says the average energy you calculate using any trial wave function will always be greater than or equal to the true ground state energy. Always.
For the goal is always to push that calculated energy down to get as close as possible to the real minimum.
Precisely. You want to find the network parameters, the weights and biases that give you the lowest possible energy estimate.
And where does the Monte Carlo part come in?
That's how you estimate the average energy. You can't possibly evaluate the energy for every single configuration of the system. There are just exponentially many.
Too many to count.
Way too many. So instead, you use Monte Carlo sampling. You generate a set of representative configurations, like different arrangements of spins on a lattice, based on the probability distribution defined by your current NQS wave function, specifically the square of its amplitude.
Ah, okay. So the network doesn't just guess the wave function, it also tells you which physical states are more likely, and you sample based on that likelihood.
Exactly. And for each configuration you sample, you calculate something called the local energy. This is a specific value you get by applying the system's Hamiltonian, its energy operator, to the NQS wave function at that specific configuration.
Okay.
Then you average these local energies over all the samples you took. That gives you a Monte Carlo estimate of the system's total energy for your current NQS guess.
Got it. Sample states based on the NQS probabilities, calculate local energy for each, average them up. That gives your energy estimate.
You got it. Then VMC uses optimization algorithms, typically variations of stochastic gradient descent, adapted for this quantum context to adjust the internal parameters of the NQS network.
and the adjustment is always aimed at.
Reducing that estimated average energy, you repeat this whole cycle. Sample, calculate local energies, average, adjust parameters. You do it iteratively, and hopefully this process drives the NQS towards representing the true ground state wave function, the one that truly minimizes the energy.
Okay, that makes sense. That's the standard picture. Now, let's get to the really new stuff, the innovation. You mentioned hyperbolic space. How is that fundamentally different from the Euclidean space our usual networks live in?
Right, so think of Euclidean space as flat, like a sheet of paper or the grid you draw graphs on. In this space, parallel lines stay parallel forever. Angles in a triangle always add up to 180 degrees.
Geometry class, basically.
Exactly. Distances work like you'd expect. If you go twice as far from a central point, the area or volume around it grows predictably, like by a factor of 4 in 2D.
Okay, standard stuff.
Hyperbolic space, though, is fundamentally different. It has negative curvature. It's harder to visualize, but think maybe of a saddle shape, or maybe more relevant for the specific model they used here, the Poincaré ball model.
Poincaré ball, what's that?
It's a way to map the infinite hyperbolic plane onto a finite disk. In this space, parallel lines can actually diverge, spread away from each other. Angles in a triangle add up to less than 180 degrees.
Less. Okay, that's weird.
It is, and distances expand exponentially as you move away from the center. Things get bigger or spread out much, much faster than in flat Euclidean space. The available space grows incredibly quickly as you move outwards.
So the geometry itself is intrinsically curved, warped in a specific way.
Yes, and the Poiret ball model is just one way to represent and compute within that curved space. Points get squished together visually as they approach the boundary of the disk, but in the true hyperbolic sense, the boundary is infinitely far away.
Okay, mind-bending. But why? Why make this leap from familiar flat space to this curved hyperbolic space for modeling a quantum system? What's the hypothesis driving this?
Well, the really compelling hypothesis comes from successes in other fields, actually, like modeling complex networks or, interestingly, natural language processing.
NLP. How does that connect?
It turns out that hyperbolic geometry is particularly good, extremely efficient at representing data that has an intrinsic hierarchical or tree-like structure.
Like, I mean, an organizational chart or species in biology, things branching out.
Exactly like that. In hyperbolic space, because it expands so quickly, you can embed tree structures with exponentially many nodes within a relatively small radius compared to Euclidean space. It's naturally suited for hierarchies.
Okay.
So the idea here, the core hypothesis, is that some quantum systems might have interaction patterns that naturally form this kind of hierarchy, especially systems where interactions aren't just between immediate neighbors, J1, but also next nearest neighbors, J2, next nearest J3, and so on.
Ah, so if the way particles influence each other branches out in layers, maybe a network that lives in a space that feels tree-like could model it more naturally, more efficiently than one stuck on a flat grid.
That's the intuition precisely. If you can map these potentially hierarchical quantum correlations onto the hyperbolic space, the network's internal geometry aligns better with the problem's intrinsic structure. You're using the right kind of mathematical space for the job.
Okay, this feels like where we get into the deeper, more academic part of the innovation. How do you actually build a neural network? Specifically, they used a gated recurrent unit, a GRU. How do you make it function in this curved space? Because, yeah, standard neural nets are all about vector addition, dot products, matrix multiplies. That's all Euclidean math.
Right, and this is really the technical heart of the paper. You can't just take hyperbolic coordinates and plug them into standard Euclidean operations like matrix multiplication or adding vectors. It just doesn't work mathematically. It doesn't respect the geometry.
So the fundamental operations themselves have to change.
Exactly. They need to be redefined for hyperbolic space. For instance, simple vector addition in Euclidean space. In hyperbolic space, you use something called Mobius addition, often written with a symbol like O plus dollar. It's a specific formula for combining points that accounts for the space's curvature, and it behaves differently. It's not commutative or associative in the standard way.
Okay, so even adding things is different. What about multiplying by a number, scalar multiplication?
Similar story, that's replaced by Mobius scalar multiplication, maybe O time dollar. Again, a different formula designed for this geometry.
All right, basic arithmetic is different. What about the more complex operations, like matrix multiplications and those nonlinear activation functions that are so crucial for neural networks?
Those also need careful adaptation, and this is where a concept called the tangent space becomes really important.
Tangent space.
Yeah, at any given point in the curved hyperbolic space, you can imagine a flat Euclidean space that just touches it at that single point, like laying a flat sheet of paper tangent to the surface of a sphere.
Okay, like a little local flat patch on the curved surface.
Exactly, and you can define mathematical mappings to move between the curved hyperbolic space and this flat tangent space at a particular point. There's an exponential map, often written dollar text, that takes a vector in the tangent space and maps it to a point in the hyperbolic space, and a logarithmic map that does the reverse.
Okay, so you can sort of step out of the curved space onto a temporary flat space, do something, and get back.
That's a great way to think about it, and this is often how operations like matrix multiplication are handled. You might map points to a tangent space, apply a standard Euclidean matrix multiplication there, and then map the result back to hyperbolic space. For nonlinearity, like real U or tan, they use what are called Mobius pointwise nonlinearities, maybe F dollar. These apply the function in a way that's consistent with the hyperbolic geometry, often involving these log and x maps too.
Wow. Okay, so the network's math isn't just happening in hyperbolic space directly all the time. It's this clever dance between the curved space and these local flat tangent spaces, performing calculations while always respecting the overall curvature.
That's a very good summary. The specific design of the HGRU takes the standard GRU equations, the ones for the update gate, the reset gate, the candidate hidden state, and meticulously replaces all the Euclidean additions and multiplications with their proper hyperbolic counterparts, using Mobius operations and these tangent space mappings where needed.
And the whole point of doing all this complicated redefinition.
The point is that the network's internal machinery is now intrinsically designed to process information and learn relationships within this curved geometry. It allows it to potentially capture those hierarchical structures we talked about more naturally, more efficiently than a standard network forced to operate in flat space.
That is fascinating. So how does this HGRU unit then get used to actually represent the quantum wave function, the NQS?
The overall architecture is often similar to standard RNN-based NQS. You have the recurrent unit, now the HGRU, processing the input sequence like spins on a chain. Its output, the hidden state, is then typically fed through one or more standard dense layers.
Okay.
For a real valued wave function, the final dense layer's output, maybe after a softmax-like activation, is interpreted as giving the conditional probabilities for the spin at each position, given the spins that came before it in the sequence.
And you multiply those together.
Exactly. You multiply the conditional probabilities along the sequence to get the total probability, p dollars, for observing a specific complete spin configuration valor. The wave function amplitude is then just the square root of that probability, squared over v.
Simple enough for real wave functions. What if it needs to be complex with phase?
They handle that similarly to standard methods too. They typically add another dense layer running in parallel, often with a soft sign activation, which outputs values between -1 and 1. This output is interpreted as being proportional to the phase angle for that configuration. You then combine this phase factor with the amplitude.
And the inputs, the spins themselves.
Usually represented using one-hot encoding. So for a spin 12 system, spin up might be 1, 0, and spin down 0, 1, fed into the HGRU at each step.
Okay, we got the structure, the tricky hyperbolic math, and the motivation, the hypothesis about hierarchy. Did it actually work? Did the hypothesis hold up when they put it to the test?
That was the crucial next step, yeah. They tested the HGRU NQS against standard Euclidean GRU, EGRU, and sometimes Euclidean RNN, NQS on several well-known prototype quantum many-body systems.
Which ones?
They used the transverse field Ising model, or TFIM, in both one dimension and two dimensions. That's a classic model with nearest neighbor interaction plus an external magnetic field.
Okay.
And they also use the 1D Heisenberg model, specifically the J1, J2, and J1, J2, J3 versions. These are great because you can explicitly add next nearest J2 and even third nearest J3 neighbor interactions, directly controlling the level of hierarchy in the Hamiltonian itself.
Perfect test beds then. So let's look at the results. First, the 1D TFIM. That's mostly nearest neighbor stuff, right? Less inherently hierarchical.
Correct. The basic 1D TFIM has a relatively flat interaction structure. And interestingly, in the tests on this model across different system sizes, they looked at Antony 40, 80, 100 spins. The hyperbolic GRU did not show a consistent, clear advantage.
Really?
Yeah, there was variability. Sometimes the Euclidean GRU or even a simpler Euclidean RNN performed comparably, or maybe even slightly better depending on the exact setup and whether you looked at training or final inference energy. It wasn't a decisive win for the HGRU when the system itself lacked that strong hierarchical character.
Which kind of supports the hypothesis in a way. If there's no hierarchy to exploit, the hyperbolic geometry doesn't give you a special edge.
That's a fair interpretation, yeah. Now, the 2D TFIM case is really interesting.
How did they handle 2D? Did they build a 2D hyperbolic network?
No, not in this work. What they did was clever. They used the 1D NQS architecture, both the hyperbolic GRU and the Euclidean GRU. But then, when calculating the energy, they reshaped the 1D spin configuration sampled by the network into a 2D lattice.
Wait, how does using a 1D network on a reshaped 2D lattice test the hierarchy idea?
Because the reshaping artificially introduces a kind of hierarchical structure from the perspective of the 1D network processing sequence. Think about mapping a 2D grid onto a 1D chain, say row by row. Spins that are far apart in the 1D sequence, like site I and site I plus n, where n is the row width, suddenly become nearest neighbors vertically in the 2D picture.
Ah, I see. The 1D network is just processing a sequence, but the way that sequence relates to the 2D interactions creates these longer range dependencies in the sequence order, which mimic hierarchy for the RNN GRU.
Exactly. The network has to learn correlations between elements that are far apart in its input sequence because they are close in the underlying 2D geometry. And here, in this setup with artificially induced hierarchy, the results were different.
What happened?
The 1D HGRU consistently outperformed the 1D Euclidean GRU. Across different 2D lattice sizes they tested, 5,7, 8,9, the HGRU got lower, better variational energies in the final inference stage every single time. And it was also better in training 3 out of 4 times.
So when hierarchy was present, even artificially, the hyperbolic network started to win.
Yes. Now, they did note that a specialized 2D Euclidean RNN architecture was actually the best overall for the 2D problem, which makes sense. But the key comparison here is between 1D HGRU and the 1D EGRU on this reshaped problem. And there, the hyperbolic approach showed a clear advantage linked to that structure.
That's pretty compelling. Okay, but the Heisenberg models, J1, J2, and J1, J2, J3, that's where the hierarchy is baked right into the physics, right? By adding those J2 and J3 terms.
Precisely. These are perhaps the most correct test cases. Let's take the 1B Heisenberg J1, J2 model. When the J2 interaction strength is 0, you just have nearest neighbor J1 interactions. Minimal hierarchy. And in that case, the standard Euclidean GRU actually performed better.
Okay, consistent with the 1D TFIM.
But as soon as you turn on J2, making it greater than 0, you add those next nearest neighbor interactions. You explicitly introduce a layer of hierarchy. And what happened then? Across various non-zero J2 values they tested, like J2 equals 0.2, 0.5, 0.8, the HGRU definitively outperformed the Euclidean GRU.
A clear switch.
A very clear switch. The tables in the paper show it plainly. The HGRU gets significantly lower energies once that J2 term kicks in and creates the hierarchical structure.
Wow. And what about the J1, J2, J3 model? Adding yet another layer of interaction range. Even more hierarchy.
This is where the difference became really dramatic, with both J2 and J3 interactions present, creating a more complex, multi-level hierarchy. The HGRU consistently and definitively beat the Euclidean GRU, and not just by a little bit, by a significant margin in all the cases they tested.
Across different J2, J3 values.
Yes, across different combinations of J2 and J3, and even across experiments where they slightly varied the network sizes. The energy plots in the paper are quite striking. You can visually see the HGRU converging much, much closer to the known exact or near exact results for these models compared to the Euclidean GRU, which often plateaued at a higher energy.
Okay, that really nails the point. So, putting it all together, the experimental results seem to provide really strong evidence for their core hypothesis, don't they? That the performance boost from the hyperbolic GRU NQS is directly and strongly correlated with the presence of hierarchical interaction structures in the quantum system. Whether that structure is built into the physics, like in J1, J2, J3, or introduced by how you represent the problem, like the 2D mapping.
That's absolutely the clear takeaway from their results. It strongly suggests that this idea of matching the geometry of your machine learning model to the sort of intrinsic geometry or structure of the physical system you're modeling, it's not just elegant, it can actually yield tangible benefits in performance.
Okay, that's the really exciting upside, better results, potentially unlocking more complex problems. But, there's usually a catch, right? What are the trade-offs? What's the downside to using these fancy hyperbolic networks?
Yeah, you anticipated the main one. While they can be powerful for the right problems, these hyperbolic networks, at least with current methods and implementations, are significantly more computationally expensive. They're much slower to train compared to their standard Euclidean
How
counterparts.
much slower are we talking? Like a little bit or?
Noticeably slower, the paper gives some concrete numbers. For that 1D TFIM with 100 spins, they reported training the HGRU took around 10 hours on their setup, like a standard laptop. The Euclidean GRU finished in about 1.5 hours.
Wow, that's like nearly 7 times slower.
Yeah, and for the 2D TFIM on a 9,9 lattice, using that 1D approach, the difference was even starker, roughly 30 hours for the HGRU versus only 3.5 hours for the Euclidean GRU.
Oof, 30
It
hours?
adds up. Those underlying hyperbolic operations, the Mobius math, the tangent space mappings, they're just more complex and computationally intensive than standard Euclidean vector math.
That's a pretty significant drawback, especially if you're tackling really large systems or need to run many training trials. Any other practical hurdles?
Yes, the optimization side is also trickier. You can't just use standard optimizers like Atom or SGD out of the box,
Why not?
because those are designed for optimizing parameters in a flat Euclidean space. Hyperbolic space is curved, so gradients behave differently. You typically need to use specialized optimizers designed for these curved or Riemannian manifolds, something like Riemannian stochastic gradient descent, RSGD.
Which probably means more complex implementation, maybe more parameters to tune for the optimizer itself.
Potentially, yes. It adds another layer of complexity to the training process compared to standard deep learning workflows.
Okay, so summarizing the trade-off, you get this higher performance potential, especially for hierarchically structured problems, but it comes at the cost of significantly increased computation time and more complex optimization procedures.
That's the current state of play, yes.
So where does this leave the field? What are the sort of broader implications and what exciting future research directions does this work open up?
I think the biggest significance is that this work serves as a really strong proof of concept. It fundamentally validates the idea that bringing non-Euclidean machine learning architectures into the realm of quantum many-body physics is a viable path forward and potentially a very fruitful one.
It's not just a theoretical curiosity anymore.
Exactly. It demonstrates that thinking carefully about the underlying geometry of the physical problem when you design your neural network ansatz isn't just an abstract mathematical exercise. It can lead to demonstrably better models for certain classes of problems.
It feels like it opens up a whole new dimension in the NQS toolbox, doesn't it? Beyond just changing layers or activation functions, you're changing the fundamental space the network operates in.
Absolutely, and that naturally leads to exciting future research avenues. One obvious step is generalizing this work, maybe developing native 2D hyperbolic NQS, like hyperbolic CNNs perhaps, to tackle 2D quantum systems directly without that artificial 1D reshaping.
Right, for a more direct comparison on 2D lattices.
Yeah. Researchers could also explore other ways to model hyperbolic space beyond the Poincare ball used here, like the Lorentz model, or even investigate completely different non-Euclidean geometries, perhaps spherical geometry, if some physical systems suggest that might be a better fit.
And what about other types of non-Euclidean network architectures? They used a GRU here.
Right, you could imagine hyperbolic versions of other popular architectures, hyperbolic transformers maybe, applying different kinds of geometric deep learning techniques to building NQS.